Alright, okay, so welcome everyone to this new video where we discuss stuff on the board. Today we are going to discuss a subject of mathematics, and that's a relatively common one, which has to do with the Taylor series. Now, depending on your background, so if you have a pre-university background, you may have very vaguely heard of this, so that can be useful for you. If you have a post-university or a university background, then maybe you have come across the actual Taylor series formula, but maybe not some sort of simple proof of it. And if you have seen the proof, then in any case, that's a good reminder about how to go about this proof. Now, by the way, this is a particular proof, I think, which is due to Taylor, but also I think Laplace or Pascal, I can't remember, but basically kind of one of the two, I think probably Laplace. And the thing is, there are multiple ways of deriving the Taylor series, and here is just one of the many ways to do so. And in fact, we'll give a kind of a name to it at the end of the derivation, because that makes more sense once we have reached the end. So basically that's it. That's what we are going to do today, is simply a quick derivation of the Taylor series. Alright, okay, so what we have to deal with, context-wise, is the following. We've got a function f, and this function f has to belong, let's say, to the C infinity class. And C infinity class is simply telling you that this is continuous, okay? But basically that the derivative, and in fact all derivatives, are continuous and differentiable as well, okay? So that's what the C infinity class means, that basically you've got a function which is infinitely differentiable and continuous. And with continuous, obviously, differentiations as well. And that's for x that belongs to some domain, and this domain is going to be a subset of the reals, and basically that's kind of the most general case you can conceive. Now that we've said that, we can kind of move on with the actual derivation. So the way it starts is kind of by writing a tautology, or something which is an identity, if you will, which is of that form. So if I write f of x, and then I want to subtract f of x from the value of f, but at some other value, which is x0, okay? Now, if I want to evaluate that stuff, then because f is differentiable and so on, what I can do is, it's also, if it's continuous, it is also integrable, and so I can write that, the f prime is integrable, so I can write the following. It's going to be the integral from x0 to x, and then of f prime. And here, just to not confuse the names that I put on the limits of integration with the integration variable, I will put a y here. So you probably remember, but just in case I will say it, that the integration variable is a dummy variable, so the actual name you give to that variable doesn't matter. So that's why I call it y here, and then x naught and x would correspond then to the limits of integration, okay? Now, what I'm going to do with that term is that I'm going to write it, basically use an integration by part. And the way I'm going to do that is simply write it this way. So maybe I can put it as an aside. I'm going to say, well, f prime, I can always write that f prime of y, I'm just trying to see where I can put that just to be sure. F prime of y, I can always write this as being y minus x, and then f prime of y, but then prime. So if I actually look at the differentiation of this stuff, I'm going to get a 1 that is coming from 1 minus x. Remember that x here is actually a constant. This is one of the limits of integration, and y is the variable. And then I need to subtract what I'm going to get from the product rule. So I'm going to get 1 times f prime of x, which is true, but then I'm going to also get y minus x times f second of y, so minus y minus x, and then the second derivative with respect to y. Okay, so I can write something like this. Okay, so because I can write something like this, I can substitute f prime of y with this expression here. So I'm going to get the integral from x naught to x of this stuff, so that's y minus x, and then f prime of y, and that's prime, and then dy minus the integral from x naught to x, and then we've got y minus x, and then the second derivative with respect to y dy. Okay? So here this is just to tell you that you can write it this way. Now it's quite common when you've got when you use the integration by part to actually set y, to get the y instead of y plus some constant. But you're going to see that this is important here. I'm just going to erase that particular expression so that I can continue the derivation just below it and it doesn't look weird. Okay, so I hope you see where this is coming from. So let's continue. So I just need to evaluate this. Now, because this is a straight derivative, I can use the fundamental theorem of calculus, and I simply get that I need to evaluate the expression in bracket here. So y minus x, and then f prime of y, and then x0 x, and then minus this integral here. So x naught x, y minus x, f second y dy. Now if I actually evaluate that stuff, then you see that when y is equal to x, that's going to be x minus x, so that's giving 0. And then what I'm getting is minus x naught minus x, okay? Minus x naught minus x, f prime of x naught, and then minus that part here, okay? So what I'm going to get is basically x naught minus x naught minus x, so I'm going x minus x naught, and then f prime of x naught, and then minus this term. Now this term I want to integrate by part again, and what I'm going to write is basically continue with my 1 minus x, and basically getting the antiderivative of it to write it in a form similar to that. So I'm going to get minus then the integral from x naught to x, and then I'm getting y minus x squared divided by 2, and then the third derivative of f, and now I need to this, so that's this kind of differentiated, and then minus, so that's a plus the integral from x naught to x of y minus x squared divided by 2, and then the third derivative of f with respect to y. Okay, so basically that's what we get. And what I can do is that because this is again a direct derivative, I can use again the fundamental theorem of calculus, and so what I'm getting, I'm going to get this still x minus x naught, and then f prime of x0, and then I'm going to get here again, I'm simply directly integrating, so I'm going to get minus, and when you look at the minus part, you're going to get again x minus x, so that's 0, okay, and so then you get minus, so that's a plus. So here we've got plus, and the non-zero term is going to be x minus x0 squared divided by 2, and then the no, my bad. Sorry. Here this was a second derivative. And then the third derivative comes from the product rule. And so here you've got the second derivative at x naught. And then you've got the remainder integral here. Okay? So plus the integral from x naught to x, and then 1 minus x squared divided by 2, and then f y dy. Okay? So essentially you probably start seeing kind of where we're going with this. You can continue basically this particular strategy with this term, and at the end of the day what you're going to get is an expression that looks like this. So that's going to be the sum. Let me write this sum a bit better. You're going to get the sum, let's say for n is equal to 1, then from 1 to n, let's say, and then you're going to get x minus x naught to the power n divided by n factorial, and then you're going to get the nth derivative of f evaluated at x naught, okay, and then you need to stop at some n, and so what we are going to get here is basically plus, and then we've got minus 1 to the power n, and then the integral from x naught to x of y minus x to the power n. In fact, here, apologies, this is the n here. Then divided by, let's check. So that's divided by n factorial. If I'm not mistaken. Then we can check after that, compare with here, right? So here you've got factor 2, and we still have the factor 2. Here you've got 2, so here 2, and then we've got the n plus 1th derivative y, and then dy. Okay. So basically, what we find here is an expression of f of x minus f of x naught. And in principle, again, of course, x naught, let me just put that a bit more aligned. So we've got f of x minus f of x naught. And the thing is, of course, x naught has to belong to the domain D of definition and so on. So that has to, this is kind of obvious. And basically that's it really. So we essentially derived here the Taylor series. And this particular final term, that's what this term here is called the integral remainder. So that's the integral remainder. Okay, that usually people would call Rn, but it depends because here we want to call it rather Rn plus 1. So that's Rn plus 1. Okay, and what we see is that there are various, one of the things that obviously this remainder has to satisfy is that the limit of Rn plus 1 when when x tends to x naught is 0. Okay, so that's a matter of course. That's one of the property. So if x tends to x0, then you're going to get 0 because the limits of integration are going to be the same. So that's kind of a matter of course, but that's a precondition for it to be true. Then the order of magnitude is going to be or at least the very first term of this magnitude is going to be of the order of x minus x naught to the power n plus 1, and then times the derivative at x naught. Okay, again, that's the order of magnitude that you're going to get, and that would come from an integration by part again. But basically here, the point is that you can calculate it explicitly. Okay, and that's one of the things that we may actually look at later on when we look at certain functions. Okay, because you can explicitly calculate the error. So you could say, oh, but I could calculate it if I know the function. I can simply subtract rather, the polynomial I've got. Well, yeah, okay, that's true. But here you can also calculate it directly. Okay, so that's how you can calculate it. By the way, you can also show with this that you're going to get, you can also discuss the convergence criteria of the series. Okay, so you can simply compare the, let's say, Rn plus 1 with Rn plus 2, or with Rn, and then realize that these terms are going smaller and smaller as x tends to x naught. Okay, so that's kind of the idea. You want to have x tending to x naught, and so usually you imagine this difference to be much smaller than 1, in which case you're going to get that these terms with higher power basically become smaller and smaller. So that's the idea. That's the only thing I wanted to do today in this video. That was a quick, simple derivation of the Taylor series, which is expressed here. Of course, the Taylor series usually is expressed as f of x is equal to f of x naught plus that stuff. But basically, that's how you would get there. And you see, it starts from very, very simple identity here. Okay, so I hope you found it useful. If you've got any questions, please put them in the comment section, and otherwise, see you in the next video.